In a controlled, sterile laboratory environment, an artificial intelligence model performs perfectly. Data scientists often present a single, compelling metric to business leadership to demonstrate this performance: accuracy. When a team reports a model can classify documents with 99.1% accuracy, it sounds like a complete, ready-to-deploy solution. That number is calculated using a validation dataset. This is a clean, highly curated batch of test data that the model hasn't seen before, but where the correct answers are already mathematically defined. Because the accuracy metric is generated entirely during this training phase, the model is simply being graded against a static answer key. It predicts 9,910 answers correctly out of 10,000, and it earns a near-perfect score. At the moment of enterprise deployment, executives assume this high score translates directly to everyday work. They expect the system will do its job correctly 99.1% of the time. The mathematical score is an illusion of safety. It grades a system that has never actually encountered the unpredictability of a live enterprise environment. Everyday corporate work is not a vacuum. The moment a model leaves the sandbox and enters a live workflow, it collides with a messy, high-velocity stream of operational data. The sanitized inputs of the lab are replaced by ambiguous document scans, novel customer queries, and simple spelling errors. Faced with these variations, the model's rigid logic begins to fracture. The immediate operational symptom is a massive influx of false positives. The system raises an alarm for every minor deviation it doesn't recognize. Surviving this transition requires a conceptual shift we call the precision pivot. We have to stop measuring model accuracy and start measuring reliability. Deploying an AI based strictly on its validation accuracy sabotages the workflow. Instead of an autonomous agent automating a process, you create a bottleneck that requires constant human supervision just to clear the false alarms. The degradation of the accuracy metric happens through three specific transformations. The first is data drift. Real-world information is dynamic, while validation data is entirely static. This 2D feature space shows a decision boundary separating two categories of data. A model builds its rules on these historical clusters. As live data enters, inputs drift away from original parameters. The rigid boundary becomes obsolete, misclassifying new patterns. The second transformation is noise amplification. Real-world data is inherently incomplete and filled with irrelevant noise. Zooming in on this decision boundary, we see the model memorized the specific noise of its test set rather than actual patterns, a phenomenon called overfitting. The third transformation is context. A 99% accuracy rate is operationally useless if that 1% of errors consistently leads to catastrophic misdiagnoses or severe financial penalties. This results in alarm fatigue. When the system constantly flags minor, context-free deviations, human reviewers become desensitized to the alerts entirely. Prioritizing raw accuracy over adaptability creates brittle models. They achieve high marks in the lab, but possess no actual ability to generalize their knowledge beyond the exact parameters of their inception. To navigate this, we apply the AI-GAGI framework. This is a structural approach designed to engineer reliability through intentional, bidirectional communication. The first pillar of this framework is calibration. We must adjust the model to account for the actual, asymmetric cost of different types of errors in a live business environment. This confusion matrix illustrates fraud detection. Incorrectly flagging a major legitimate customer, a false positive, causes severe reputational damage, costing far more than missing a minor fraudulent transaction. We actively tune decision thresholds to strictly minimize these highly damaging errors. The mathematical reality of this calibration is that the model's overall accuracy score will drop slightly. Sacrificing a few percentage points of lab accuracy is the pragmatic cost of protecting the enterprise's operational flow and client relationships. There is a severe operational risk when a model attempts to process highly ambiguous data it has never seen before by simply taking a guess. The second pillar relies on confidence score thresholding. This is the mechanism that allows a reliable model to know what it doesn't know. This probability distribution curve shows how the system evaluates the mathematical certainty of its own prediction. The trailing edges represent low confidence inputs. When a reliable model confronts these low-confidence inputs, it triggers a graceful fallback protocol. Instead of generating a guess, it pauses and routes the data directly to a human expert. A brittle model blindly guesses on a novel scenario, occasionally getting it right. It maintains its accuracy score while entirely failing operational predictability. A truly reliable AI is defined by its structural capability to safely raise its hand and signal that it lacks the context to proceed. Once the graceful fallback occurs, the human expert steps into the loop to review the novel data the system couldn't process. The expert's job here requires more than basic correction, simply providing the right answer. The third pillar utilizes a process of active instruction. This flowchart demonstrates how the expert feeds the shifting context and new parameters directly back into the model's underlying logic, reshaping its decision boundaries. This creates a high-fidelity communication channel. Human intuition and machine precision engage in a constant, reinforcing handshake. This bidirectional instructional loop is the engine of reliability. It transforms a decaying model into a robust system that grows stronger with every edge case it encounters. A stabilized AI architecture consists of a core model fortified by cost calibration, confidence thresholding, and continuous instructional loops. This shifts the metric of enterprise success to reliability, the mathematical probability of producing high-fidelity, actionable outcomes amidst uncertainty and noise. A brittle model introduces chaos and constant supervision. A reliability-engineered system delivers steady, predictable throughput for everyday corporate work. Abandoning the vacuum of validation metrics requires a strategic pivot from business leadership, moving past the appeal of a perfect lab score. By escaping the accuracy trap, organizations can deploy resilient, autonomous agents capable of thriving in the messy, dynamic reality of the modern enterprise.